Hello everyone, this is lecture 16, span and set. In this lecture, we're going to revisit the concept of linear combinations of a set of vectors in a vector space V. And later on, we're going to use this concept, linear combinations, to build up another concept called the span and set of V and the idea of the span of a set. Okay, so why do we need to learn about linear combinations in addition to learning the theory of span and set and the set of a span of a set? Actually, there's an application in reverse problem that most of us kind of aware of. Is that of the screen or the color on the screen of the phone that you're using or the colors of the monitors that you're looking at in your computers. Is actually there's three basic colors that generate all the colors that you can see on the screen or on your monitor. That is, the three colors are red, green, and blue, right? Using these three basic colors, you can actually generate all the colors that you can see on your monitors, on your screen of the phone. At here, this on the right hand side, I have the web page here. So this is the red colors, right? Like this vector consists of three components, right? So if this component equal to 25500, so this is purely red, this particular vector will indicate purely green color, and this vector W indicate purely blue colors. And if you want to generate this particular vectors, right, or this particular colors, and this colors is a linear combination of the three colors, red, green, and blue. Okay. Let's say you want to generate a white color on the screen. What you do is you can modify this particular value, right? So the coefficients A, B, and C, or in this case, D is the linear combinations of the three vectors U, V, and W. For A, B, C are just some constants, right? So let's change the value of A, B, and C. Now, as you can see, if I move C to 1, the coefficients A equal to 1, B equal to 1, C equal to 1 will help me generate a white colors, right? This particular vector here. Now, if I want to generate a black color, so I can move the coefficients or modify the more coefficients so that I have, as you can see, the vectors get smaller and smaller, and this becomes 0, right? So the vector 0, 0, 0 will indicate that I can use the red, green, and blue to generate a black color. And again, for any colors that you can see, or color pixel that you can see on the screen of the computers or the screen on your phone can be generated using these three colors, red, green, and blue. So that's the idea of the linear combinations that we see in reality. Another concept for similar to this colors on the screen of the monitor or the screen of your phone is actually the printing the color in the printing machine or in the printer, right? They don't use these three colors, right? They don't use red, green, and blue. Actually, all the colors that you see in the color printer is actually generated by a linear combinations of these following colors. So this is the pack of the colors toner, right? That you put that into a printer, right? This should be right. All the colors that you see in a printout or that you use in the printer is the linear combinations of the three main colors: cyan, right, magenta, and yellow. All right, so that is very that's the idea, right? So using the screen, you have one set of colors, right? Red, green, and blue, and all the colors can be written as the linear combination of these three colors: red, green, and blue. But for printing, right, or when you use a color printer, it is all the colors generated by these three colors: cyan, magenta, and yellow. Or all the colors can be written as linear combinations of cyan, magenta, and yellow. And in addition to that, you need to add a fourth color is for true black color. And this true black, let me use this particular website. Will help generate the black ink in your printout. All right, so for this particular case, you have four colors: cyan, magenta, yellow, and black. Right, it depends on the percentage of each colors. You will have a different colors. Right? Or in other words, one color can be generated as linear combinations of cyan, magenta, yellow, and black. So in this case, if you put 100% of cyan, 0% of magenta, yellow% of yellow, and 0% of black, you have cyan, true cyan. If you get 0 cyan, 100% of magenta, 0 yellow, 0 black, you have a true magenta. Right? If you get 0 cyan, 0 magenta, 100% of yellow, and 0 black, you have a true yellow. And then, of course, if you put 100% black, then you have a true black. You can generate all the colors using the linear combination of these four colors for your printout. Right, so let's say I have 50% of cyan. I have this 30% of magenta, and let's say 0.5 or just 5% black color. So this is sky blue. That's the color generated by this linear combinations of these three colors. All right, so that's a fun way to think about linear combinations, right? Because you can use, right, depends on the machine or the type of machines that you have, you can have a different linear combinations of colors, right? If you look at the screen on your phone or your monitors, then all the colors can be generated or can be written as linear combinations of red, green, and blue. For printers, color printers, or your color printout, all the colors can be written as linear combinations of cyan, magenta, yellow, and black. Okay, so that's the fun way to think about linear combinations in the real world applications of linear combinations. So let's go back to the theory and then try to build up the linear combinations concept one more time and use that to extend that into the idea of spanning set or the span of a set. All right, so let me close this out. So first, linear combinations of vectors in a vector space. A linear combinations of the vectors v1, v2, vn in Rn is the vector v of the form v equal to c1 v1 plus c2 v2 up to c plus cn vn, where c1 c2 up to cn are real scalars. All right. In other words, you say that V is written as linear combinations of V1, V2, Vn. If C1, there exists the real scalar or the real coefficient C1, C2 up to Cn. All right. So for the following example, we consider the set of vectors 1, 3, 1, 0, 1, 2, 1, 0, negative 5 in R3. And we say that the vector v1 So let me denote that this is vector v1, this is vector v2, and this is vector v3. So the vector v1 can be written as a linear combination of vector v2 and v3 as v1 is equal to 3 times v2 plus v3. Or if you do a quick calculation, you will see that 3 times v2, which is 0, 1, 2, plus v3, which is 1, 0, negative 5, will give you 0, 3, 6, plus 1, 0, negative 5, or this is equal to 1, 3, and 1, which is exactly equal to the given vector v1. And you may wonder how can I find 3 here, and how can I find the coefficients of v3 to be 1? We will learn how to do that later on in this lecture, of course. But for now, it's just the idea I want to give you again, that a vector can be written as linear combinations of other vectors, right? So in this case, v1 can be written as linear combinations of v2 and v3. In the next example, I have a set of matrices, so 2 by 2 matrices. Let me call this matrix C's to be, this is M1, M2, M3, M4. Okay. And in this particular example, I say that M1 can be written as a linear combinations of M2, M3, and M4 as, so M1 is equal to M2 plus 2M3 minus M4. A quick calculations give us 0 to 1, 0 for M2 plus 2 times M3, which is negative 1, 3, 1, 2 plus negative 2, 0, 1, 3. Yeah, if you do, so now this is constant multiple of a vector of a matrix, give you negative 2, 6, 2, 4 plus negative 2, 0, 1, 3, right? And therefore M1 is going to be equal to 0, 8, 2, 1. Okay. And again, to find the coefficients of this linear combinations, we will learn how to do that in the next example. All right, so we want to, in example 3, we want to write the vector W as linear combinations of the vectors in the polar inset 1, 2, 3, 0, 1, 2, and negative 1, 0, 1. Right. Now to write W, let me be careful here. So to show W can be written as linear combinations of the vectors in S, right? Let me denote that the vectors in S to be W1, this is W2, and this is W3. All right. What you do is you need to find the coefficients C1, C2, and C3, right? So to show W can be written as a linear combination of the vectors in S, we need to determine the real scalars C1, C2, C3 such that W can be written as C1 times W1 plus C2 times W2 plus C3 times W3. Right. We know the value of W. We know the values of W1, W2, and W3. Going to put everything into this vector equations and see what we got. All right, so I'm going to switch the equal sign around. So instead of W equal to this linear combination, I'm going to write the linear combinations equal to W. So it's the same thing. Okay. So I'm gonna substitute vector W, W1, W2, and W3 into these equations I get. So C1 times W1 is going to be 1, 2, 3, plus C2 times W2, 0, 1, 2, plus C3 times W3, negative 1, 0, 1. Right. Move this out of the way a little bit. This is equal to W to be 1, 1, 1. Okay, so now I'm going to distribute C1, C2, and C3 into the component of the corresponding vector. Or this is the scalar multiple of vector, scalar multiplication of vector, scalar multiplication of vector. So I got C1, comma, 2C1, comma, 3C1, plus 0, comma, C2, comma, 2C2, plus negative C3, 0, C3 equal to 1, 1, 1. Right. So from here, you combine the three vectors together using additions. And you have C1 plus 0 minus C3, comma 2C1 plus C2 plus 0, and 3C1 plus 2C2 plus C3 is equal to 1, 1, 1. And these equations give you a system of three equations with three unknowns, right? So the first component on the left equal to the first component on the right. The second component on the left equal to the second component on the right. And the third component on the left equal to the third component on the right. So we obtain the following system of equations. You have C1 minus C3 equal to 1. That's the first equation. Second equation is 2C1 plus C2 equal to 1. And the third equation is 3C1 plus 2C2 plus C3 equal to 1. Right. So when you talk about linear combinations and we want to know if a vector can be written as linear combinations of other vectors, you just perform these calculations. Set up this equation, substitute the value of vectors that you know into the equations, and you're going to obtain a system of linear equations. In this case, you have a system of three linear equations with three unknowns. And at this point, hopefully you know how to perform this particular calculations to obtain C1, C2, and C3, right? At this point, there are many ways for you to calculate the solution of the system. Again, either you can use eliminations method or substitution method. You can use Gauss-Jordan eliminations method. You can use Grammer's rule to evaluate the solution of the system. Or you can find the inverse matrix of the coefficient matrix and use the idea of x equal to A inverse times B to obtain the solutions, right? There are many ways at this point to get the solutions, but what I'm going to do is I'm going to use Python and to aid with the calculations. And to use Python, I need to turn this matrix into, this system into an augmented matrix. Use Python to reduce that to a reduced row echelon form, and see if I can get the solutions to the system. Okay, so let me rewrite this at the augmented matrix for the system. So the augmented matrix of the system is, as you have 1, 0, negative 1, 2, 1, 0, 3, 2, 1, separated by a vertical line, and the constant matrix is 1, 1, 1. Okay, now I'm going to use Python to aid with the calculations. All right, let me turn to Python. So on the left-hand side, we have a lecture note. On the right-hand side is the Jupyter Notebook environment. This particular code, I just make a copy and paste from lecture 6. So there's nothing new here. The only thing that I need to modify is the augmented matrix, right? And this augmented matrix has 3 rows and 4 columns, right? So I'm going to modify, everything's going to be the same. The first 2 lines of code are going to be the same. I didn't make any changes there. The last line of code is just for me to perform the reduce row echelon form. Right. The only change that I need to make is the augmented matrix. All right, so I call my augmented matrix to be C, and I change. So here, array, open close parenthesis, open close brackets, and on the rows will occur inside this brackets. Right. So the first row, open close bracket, the first row is going to be 1, 0, -1, and 1. Now separate the first row with the second row by separate the first row and the second row by the comma. Hit enter to go to the next line, open and close another bracket. You have the entry on the second row to be 2, 1, 0, 1. And to separate the second row and the third row with a negative, then go to the next line, open and close bracket. The entries are 3, 2, 1, 1. Okay, now just hit shift enter and it will produce a reduced row echelon form. All right, so I now go back to my lecture note. I'm gonna type, or I'm gonna write my reduced row echelon form. Right, so 1, 0, -1, 0, 1, 2, 0, 0, 0. Right, and that's the constant matrix is 1, -1, 0. So that is the reduced row echelon form. Right, so this is reduced row echelon form. All right. So this reduced row echelon form is the augmented matrix of the system. Now you use this augmented matrix or reduced row echelon form to write the system. So the system becomes x1 minus, sorry, we are using C. So C1 minus C3 equal to 1. Then C2 plus 2C3 equal to -1. So we obtain this system. And from the system, we can solve for C1 and C2 in terms of C3. So that means C3 is a free variable. Right? So it also follows that the system has infinitely many solutions. Right, so from here, we can have that C1 is equal to 1 plus C3, and C2 is equal to -1 minus 2C3. Right. And again, C3 is the free variable in this case. And if we let C3 equal to some constant or some parameter T, for T is any real numbers, then we have that C1 is equal to 1 plus T, C2 equal to -1 minus 2T, and C3, of course, is equal to T, right? And of course, again, there's any, for this choice or for this system, we have infinitely many solutions. And therefore, it's show that this vector W, can be written as linear combinations of the three vectors in the set S, right? And we can, let's say, assume that we know the parameter t, right? For example, let's t equal to 1. And that's one solutions that help us write W, vector W, as linear combinations of the three vectors W1, W2, and W3. Right, so so in this case, we can say, suppose t is equal to 1, then you'd have that C1 is equal to 2, C2 is equal to, so 1 is -3, and C3 is equal to 1. Then W can be written as 2 times W1 minus 3 times W2 plus W3, like that. So W can be written as linear combinations of W1, W2, and W3. Similarly, we move to the next example, and we want to know that can the vector W of the form 1, -2, 2 can be written as linear combinations of also the three vectors in the same set, the set S, right? So we're going to follow the same procedure as the previous example, that we're going to set up a vector or the vector equations that we suppose W can be written as a linear combinations of W1, W2, and W3, right, and see what happened. Right. So suppose W can be written as a linear combination of W1, W2, and W3. So that is, and there exists C1, C2, C3 such that W is equal to C1 W1 plus C2 times W2 plus C3 times W3. Okay, so with the setup, and we know the form of the vectors, right? We know W, we know W1, W2, and W3. I'm gonna plug them into these equations. You get this is 1 comma -2 comma 2 equal to C1 times 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times -1 comma 0 comma 1. All right. And from here, you can form a system of linear equations with three equations with three unknowns, C1, C2, and C3. So the first equation is that of C1. So we obtain the following system. So we got C1, right, 1 times C1 plus 0 times C2. So plus 0 times C2 minus C3. Right, so minus C3 is going to be equal to the first component of W, which is equal to 1. Right, and we're going to follow with the second equation and the third equation in the same manner. That is, so 2 times C1 plus C2 plus 0C3 equal to -2. And the last equation is 3C1 plus 2C2 plus C3 equal to 2. Okay. So now we have the system. Again, at this point, we have so many ways to solve the solutions of the system, but I'm going to use Python to aid with the calculations, right? To save time, and because I just want to bring in the idea of linear combination instead of solving the system. Okay, so let's move to Python. So we're going to modify the code. So just for this particular line of code, right? So let me change this to C, And the system or the augmented matrix of the system is going to be 1, 0, negative 1, 1, right? So if you notice between example 3 and example 4, everything's going to be the same except for the right-hand side of the system. Okay, so the second equation is 2, 1, 0, and here is negative 2. The third equations, the coefficients are 3, 2, 1, and positive 2. And we're gonna hit Shift Enter, and this is what we're going to see. So I make a mistake here. So I changed the matrix into to C instead of A. So this has to be matrix of C. Right? So hit Shift Enter, and this is the reduced row echelon form that we're going to obtain. So the reduced row echelon form of the augmented matrix of the system is going to be 1, 0, negative 1, 0, 0, 1, 2, 0, 0, 0, 0, 1. Right? And from here, we can write down the system of this reduced row echelon form. Or if you notice that for the last row of the reduced row echelon form, it's going to give you a false statement, right? Because the 0 on the left-hand side not going to be equal to the 1 on the right-hand side. All right. But let's write down the system and see what we got here. So C1 minus C3 equal to 0. C2 plus 2C3 equal to 0, and 0 equal to 1, right? So 0 C1 plus 0 C2 plus 0 C3 equal to 1, which is a false statement. Right? And because it's the false statement, we're going to say that there's no solutions to the system, right? So there's no solutions to the system. Then C1, C2, and C3 does not exist, do not exist. And therefore, W cannot be written as a linear combinations of C1 of W1, W2, and W3. All right, so let's give you the idea of how could you actually write a vector as linear combinations of all the vectors. It's actually very helpful for us to define something called the spanning set, because this is the set of, or rather a subset of a vector space where is contained for every vector in the vector space can be written as linear combinations of the vectors in the subset S. All right, so let's write down the definitions. So I have a set S equal to V1, V2, O2, say Vn. All right, so I have n vectors in this set. Now I let this set be a subset of a vector space V. Right. The set S is a spanning set of V when every vector in capital V can be written as a linear combination of vectors in S. Right. In such case, it is said that S spans V. Okay. Again, let's recap what we just wrote down here. So S is a subset of a vector space, right? So this S contains, let's say, n vectors or some vectors, right? And if you choose any vectors in the vector space V, let's say I have a vector U in the vector space V, then every vector in V, in this case U, can be written as linear combinations of the vectors in S. Right? So in the first example, or rather this example 3, right, I have a vector W, right? So this vector, this is a three-dimensional vector, right? So this is the vector in R3, right? This vector can be written as linear combinations of W1, W2, and W3. Right? Because of that, this is called the spanning set. And it is also said that S span the vector space R3. Okay, so there are two things that we draw from this after the definition is that this S is the spanning set. Right, because again, for every vector in R3, in this particular case, W can be written as linear combinations of W1, W2, and W3. Right? Therefore, we say that S is a spanning set. And the second conclusions, we can also say that S spans V. All right, so that's the two concepts that we just wrote down. In this example 4, because W cannot be written as linear combinations of W1, W2, and W3. So therefore, S is not a spanning set, right? So in general, after this two example, in general, S is not gonna be the spanning set, or S cannot span the entire R3, right? Because go back to the definitions one more time, every vector, right? So we just proved that one vector can be written as linear combinations of W1, W2, and W3, but there is also a case where W cannot be written as W1, W2, W3. So in general, this particular set is not going to span the entire R3. Okay. So let's take a look at this following example. Right, so we want to describe the span of the set of the standard unit vectors. Right, so the standard unit vector is the vector. This is the vector in the x directions, and this is the vector in the y directions. And in mathematics, usually denote as E1, and this is E2. Okay. So this particular set consists of two standard unit vectors. So the unit vector again is the vector with length 1. So the standard unit vector in the set E1, E2. So the span of S is all of 2D plane, or R2, right? The reason is that given any vectors in R2, we can always just be able to describe the vectors as a linear combinations of E1 and E2. All right. So give me any vectors, right? So for example, I have a vector of the form 4, comma 2. Or I can write this in a column vector to match with what we have over here as column vector. So this column vector 4, comma 2 can be separated into a sum of two vectors. So that is 4, 0 plus 0, 2, right? Or rather, this is 4 times the vector 1, 0 plus 2 times the vector 0, 1. Right. So this is 4 times E1 plus 2 times E2. Therefore, 4, comma 2 can be written as a linear combination of the standard unit vectors in the set S. Right. Now, a more general case is that you have a vector of the form x, comma y. Or rather, this is the form x, y in the column vector form. You can write this as x 0 plus 0 y, or this is x times 1, 0 plus y 0, 1. Right. So x and y in this case are any real numbers. Right? And the vector column xy can be written as a linear combination of the standard unit vectors. So therefore, you say that the set S span the entire two-dimensional plane, or R2, right? Now, similar definitions or similar approach for the next example, that you have three standard unit vectors for the case of three-dimensional space, right? So the set S consists of three standard unit vectors, E1, E2, and E3. Right. Now, given any vectors in R3, right? So suppose, or given any vectors U of the form U1, U2, and U3 in R3, right? U can always be written as a linear combination of E1, E2, and E3. That is, right, if you write U1, U2, U3 in this form, you can separate this particular vector into a sum of three other vectors. Right, so U1 times 1, 0, 0 plus U2 times 0, 1, 0 plus U3 times 0, 0, 1. Okay, and 1, 0, 0 is E1, 0, 1, 0 is E2, and 0, 0, 1 is E3. So therefore, you say that this is U1 times E1 plus U2 times E2 plus U3 times E3. Therefore, we say that the set S spans R3. Right. So the set consists of standard unit vectors. Again, the standard unit vectors is the vectors in the x directions, the vector in the y directions. In the case of three-dimensional space, you have this is the unit vector in the x direction, the unit vector in the y direction, and this is the unit vector in the z directions, right? And this set consists of standard unit vectors span the entire R3, right? Or in this case, the sets span the entire R2. Okay, now moving on to the next example, right? So in the last two examples, you have standard vectors, or standard unit vectors. Now we're gonna look at some non-standard unit vector. Right? Can you actually find something? Can you actually describe the span of the set, right? In this particular case, that show that the set S consists of this vector span the entire R3. So when you look at this set, it looks like you have a similar problem to example 3 and example 4, but you have to be careful here because the vectors are a little bit different. So even though in example 4, we have example 3 and example 4, we have the vectors to be 1, 2, 3, 0, 1, 2, but the third vector now is negative 2, 0, 1 instead of negative 1, 0, positive 1. So that's a slight difference there, slightly different number. Okay, so this is a different set than the one we considered in example 3 and example 4. All right, again, we're going to use the definitions of spanning set to look at this or to solve this particular example. That for the definitions, from the definitions, we got that for every vector in R3, right, that particular vectors can be written as the linear combinations of the vectors in S. Right? If that is the case, S is the spanning set, or S span the vector space. All right, so now suppose U equal to U1, U2, U3. I don't know exactly the value of U1, U2, and U3, but what I know is that I will have a three-dimensional vectors, and I want to find a way to show that this vector can be written as linear combinations of the three vectors in the set S. Okay. All right, so suppose U is equal to U1, U2, U3 in R3. Right. So to show that S spans R3, we need to show U can be written as a linear combination of, let's say, V1, V2, and V3, vector V1, vector V2, and vector V3 in S. Right. So let me name this vector V1, vector V2, and vector V3. All right. So that is, there exists some constant C1, C2, and C3 such that, so ST again is such that U is equal to C1 times V1 plus C2 times V2 plus C3 times V3. And we know the form of U. In this case, is going to be U1, U2, U3. V1 is going to be 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times V3 is going to be negative 2, 0, positive 1. All right, so from here, from this vector equations, we're going to form a system of three linear equations with three unknowns, C1, C2, and C3. Right? And again, in this case, even though we don't write down the explicit value of U1, U2, and U3, we suppose that we know the value of U1, U2, and U3, right? The unknowns are C1, C2, and C3. All right, so we obtain the following system. That we have C1 plus 0 C2 minus 2 C3 equal to U1. 2 C1 plus C2 plus 0 C3 is equal to U2. And 3 C1 plus 2 C2 plus C3 is equal to U3. All right. Even though we don't actually know exactly the value of U1, U2, and U3, we still be able to determine if there is a solution to the system. That is, if C1, C2, C3 exist. Now there is a theorem in lecture 11, right, when we learn about properties of determinants. There's one property, where there's one theorem that's equivalent conditions for a non-singular matrix. In this theorem, there are of course, 6 different properties, but we drop the number 5 and number 6. It say that if A is invertible or the coefficient matrix is invertible, the determinant of the coefficient matrix is different from 0. And if the determinant of the coefficient is different from 0, the system AX equal to B has a unique solution for every column matrix B of the sign n by 1. So in this case, in our problem, we want to find the determinant of the coefficient matrix. If the determinant of the coefficient matrix is going to be different from 0, we can conclude that the system, this system has a unique solution. That is C1, C2, and C3 exist. And if C1, C2, C3 exists, then you can find we can conclude that the set is a spanning set, or the set S is, or the set S span the entire R3. Okay, so the job now is to look at the coefficient matrix, find the determinant of the coefficient matrix, and hope that we have a non-zero co-determinant for the coefficient matrix. Okay. All right, so now we will turn to Python to help us with calculate the determinant of the coefficient matrix. So the coefficient matrix that we got here is going to be 1, 0, negative 2, 2, 1, 0, and 3, 2, 1, right? So I call the coefficient matrix A right here, right? And I set up the matrix. Now remember, this is just the coefficient matrix and not the augmented matrix. Okay. A command for us to calculate the determinant of a matrix is going to be, right? So lin alg, this stands for linear algebra, right? So lin alg dot det of A, right? So well, we're going to use the package linear algebra in Python to calculate the determinant of the matrix A. And then shift enter. Right, so this is almost equal to -1, right? So which is different from 0, right? So let me write this here. So the coefficient matrix is going to be coefficients matrix is A equal to 1, 0, -2, 2, 1, 0, 3, 2, 1. Right, and from here you can calculate the determinant of A using Python, and it showed that the determinant of the coefficient matrix is different from 0. So therefore you conclude that, so since the determinant of A is different from 0, the solutions of the system exist, or C1, C2, C3 exist. And that is, or that means, U in this case can be written as a linear combination of V1, V2, and V3. Okay. So that's it for this example. Now there's a graph of this 3 vectors V1, V2, and V3 show here, and they have different color for the different planes that the vectors lied on. And because they lied on different they lied on different plane. Because of that reason, we can have the set to be a spanning set, or the set span the entire R3. Now, in the next example, you will see that the 3 vectors are going to lie on the same plane. And because they lied on the same plane, they cannot span the entire R3. Okay. So let's move to example 8. So in this example, we have this set of 1, 2, 3, of the set of vectors 1, 2, 3, 0, 1, 2, and negative 1, 0, 1. So these three vectors are the same with the vectors we consider in example 3 and example 4. Right. So we can say that from example 4, since the vector w equal to 1, negative 2, positive 2 in R3 cannot be expressed as a linear combinations of vectors in S, then S is not, or S does not span R3. All right, so again, the result is from example 4. All right. Now, if you want, you can actually follow the same procedure that we did in example 7. We set up the system of equations, right? Or we consider any vector u of the form u1, u2, and u3. And we assume that, okay, at first u can be written as linear combinations of the vectors in S. Then you set up the system, you obtain a system, write down the coefficient matrix and calculate the determinant of the coefficient matrix. If it's different from 0, it's going to be that the solution has, or the system has solutions, or C1, C2, C3 exists. If the determinant is equal to 0, then the solution does not exist. Okay, so let's quickly do that here. So the setup, everything's going to be the same except for the last vector, or rather the first component of the last vector changing from -2 to -1. All right, so with that small change, let's see what happens. So I'm just going to change my coefficient matrix to 1, 0, -1, 2, 1, 0, and 3, 2, 1. And if you hit Shift Enter, you can see that the determinant of this matrix is going to be equal to 0. So this is e to the -16, e to the -16. So it's a very, very small number, very close to 0. Right? And because of the determinant equal to 0, the system does not have any solution or no solution, right? Therefore, W, or the set is not a spanning set, or does not span the entire R3. Okay. All right. So I have one more definitions and one more theorem to give you in this particular lecture. So the definition is the definition of a span of a set. Right? So previous above, we actually write down the definition of a spanning set. Right? So S is a spanning set, or S span the entire vector space. So in this case, we have a span of a set. Right? Let's see what happened. So if S equal to vector v1, v2, up to vn is a set of vectors in a vector space V. Then the span of S is the set of all linear combinations of the vectors in S. Right. So it's denoted as span S equal to the set, right? So in curly bracket of C1 V1 plus C2 V2 of 2 plus Cn Vn, right? Given that C1, C2, Cn are real numbers. All right. And usually we denote the span of a set is this, right? Span S, or span of V1, V2, V3, up to Vn, right? Okay, so that is the definition of the span of a set, right? So if you have a set of vectors, then the span of that set is going to be also a set, right? But this set is the set of all linear combination of the vectors in S. All right. The next theorem is the span of S is a subspace of V, right? So if S equal to V1, V2 up to Vn is a set of vectors in a vector space V, then span S, right? So again, span S is the set of all linear combinations of the vectors in S, is a subspace of V, right? So to prove that the span S is a subspace of V, what we're going to do is that we're going to show that the zero vectors is in the set S, right? And the vector it has to satisfy two conditions, that S span of S is closed under vector additions, and the set is closed under scalar multiplications, right? To be able to show that the span of S is a subspace of a vector space, right? Even though I write the proof here, I'm gonna omit the proof for this particular theorem, and stop the lecture at this point, right? So again, we just on this page, just want to give you a quick definition of the span of a set, and say that the span S is a subspace of the vector space V. All right, so that's it for me. In this lecture, we look at the concept of span and set. And to actually write down the definition of the span and set, we look at the notions of linear combinations and how to actually find the try to determine if a vector is or can be written as linear combinations of all the vectors. Okay, so that's it for me. Please let me know if you have any questions. Thank you.